innovation, because manufacturing tests, you're not dealing with conformance, things you have to do. Really, with manufacturing, you just want to know that you've built the thing properly, that you've screwed it together properly, you've bonded things together properly, and it's all working nicely. So you don't necessarily need to make all these full characterizations, you just need to make sufficient measurements to say, yes, this is a good device. Now, you've got an antenna array. You want to know if the if the gain and phase states which control the beam are working properly. You want to know if there's any sort of manufacturing faults which are preventing that from happening. So, and then of course we have this, the challenge of dropping the cost of test. It's not just dropping the cost of test a little bit, it's dropping the cost of test dramatically compared with what we do today, which is less complex. So it's like a double whammy. You're trying to go in two directions at once. So we think that this is really where these innovative solutions will come into play, and we're having a good deal of fun in Keysight dreaming up some new solutions there. Again, if you want to talk to me later, then come see me, and we'll sign an NDA and talk all about it. But really, that has to be small, has to be scalable, has to be ultra fast, has to be repeatable, and that's it. That's the end of my little bit on fluid test. Thank you. Over to Randy again. Apologies for the little changes there.
Dropped an E.
Dropped an E,
Okay. All right, so now we will zoom into the final section. Yes? So exciting. So we're going to cover now a little bit of the system optimization and all the things we need to consider to make one of these systems sing with the best performance. Okay, so where do some of the problems originate in when we think about generating signals and analyzing signals? So the first one here on the signal generator side, or any device really that's using an IQ modulator, IQ modulators have a number of undesirable properties, although they are fantastic for manipulating both the amplitude and phase of something to do modulation, vector modulation. They do have these DC offsets, gain imbalance, cloud share, timing skew, which can degrade performance. Normally, we would say kind of today, generating signals at RF, pretty straightforward. Everybody can do it. It's not much of a mystery. When we go to the wider bandwidths and these really high frequencies, it becomes more of a black art. The things operate differently, not as you would expect. If we took a narrow slice of something that was, say, 20 megahertz wide, like as a single channel of LTE, and you looked at the amplitude and phase response, it would be very flat, very linear in phase. But if you increase the bandwidth and looked at some of these systems, you might see there's significant changes in the response over that frequency. And so this is important to consider. So these things here that I'm talking about can be calibrated out of the system, and they can be also manually adjusted for good performance. Phase noise can also be a problem. Normally the test equipment has very good phase noise, and we have options for even better phase noise performance on many of the instruments. Phase noise can be an issue for some types of modulation, like OFDM, where we have very narrow spaced subcarriers. Although at the higher frequencies, we tend to see the subcarrier spacing is wider, and the phase noise then would be, the close-in phase noise would be less of an issue. It's hard to get the phase noise close-in lower usually. Distortion, usually not a big problem in the test equipment because we understand and know how to drive everything and keep everything in the linear region. So this is not usually the problem. Signal to noise ratio is a big problem. As I mentioned earlier, when we go to the wider bandwidths, the power spectral density decreases, and now our range from the signal to the noise floor is lower. And we need to make sure through the whole process we're preserving the signal to noise ratio, because once noise gets into the system, you can't get rid of it. And as I showed that picture earlier, right, where we had that elaborate setup to do some of those extremely wide bandwidths at the high frequencies. You can imagine there's signal levels that could be adjusted up or down at each of those stages. And if you give up dynamic range earlier in one of those stages because you don't have something adjusted right, you're not going to get that back. So this is an area to always be aware of and concerned with. The amplitude flatness and phase linearity of the system, so how does the channel response vary over the bandwidth, can be a problem. Usually in receivers, we have equalizers that will correct this, but if we want to really understand the performance with the test equipment, we want to make sure that that has a flat response, so we're making sort of metrology grade performance. And then lastly, I put here test equipment optimization. And what do I mean by that? So, normally at Keysight, we design things to make them easy to use, so you just turn them on and do what you need to do, and off and away you go. But it's always generally helpful if you understand a little bit about the architecture of the instrument that you're dealing with. That always helps you understand how to use it better. Just like a car, there's many features in cars. All cars are a little different, and the more you understand about where the gear shifter is and how many gears there are, enable you to operate it better and more safely. So the same thing goes here. Understanding the architecture of the instrument and its data sheet can help you get the best performance out of it. Okay, so we'll take a quick look at the source errors in an IQ modulator briefly. So here we have a signal generator frequency response over some bandwidth. You can see the bandwidth is quite wide, and I'm showing it's maybe looks pretty flat in this region, but if we go to out and we go to a wider bandwidth, we can see that maybe it rolls off, and maybe that roll off isn't symmetric. That can cause problems. So we have the magnitude and phase, the overall magnitude and phase response. The signal that we're generating here, that we want to generate within some bandwidth, within the signal generator bandwidth, maybe is this gray signal. But if the IQ modulator is not perfectly balanced in amplitude quadrature, we will have an image that shows up. And normally that's hidden because the carrier here is centered at the center frequency, but this will degrade the quality of the signal and impair the overall error vector magnitude. If they're DC offsets, we'll end up with a CW signal at the center frequency, which is also undesirable. Okay, so if we think about that for a moment, if we had a gain imbalance, that would be, we could have an error that looked like this, where we'd have, say, the I or the Q signal had higher gain than the other one. We would have an offset either up here or below here. And you can imagine, okay, if I could, on signal generators, you often have a control to control the gain balance. So you can imagine in your head, I'll just decrease the I or Q gain to bring this back to 0 so that the response is perfectly the same between I and Q. And you could do that. But consider this. Now I have, what if I had a gain imbalance that looked like that, which was a function of frequency? Uh-oh. Now there's no single number, or no single lever I can adjust to make this be perfectly flat. The best that I could do is to center this line here so it crosses through the origin. So that's maybe better, but it's not perfect. And then you could even imagine maybe the situation's worse than that. Maybe it actually has some ripple to it, so it's not just a constant error versus frequency. Okay, so with you could manually adjust this so it was back at the center, but not perfect. You could also have the same thing with phase. Phase is a little easier to deal with, but a little harder to measure quickly. So here again we have some phase difference between I and Q that is changing as a function of frequency. But you can see there's some offset and there is some angle here. And these two can be adjusted. So the quadrature angle affects how far off this is misaligned from the origin, and the time skew is this angle here. So by adjusting those two controls, you can make this perfectly flat. Well, not flat. If there was some ripple on there, you would still have the ripple, but you could bring that line back down to the origin. So that's what you can get with best manual adjustment. Okay. Now the other one is this LO feed through, and what is that all about, and where does that come from? So I showed this briefly, but I'll show you how that works. So here again is the signal that we're generating, and underneath that we have the DC offsets, or the LO feed through, due to the DC offsets on the IQ modulator. If you were clever, you might say, well, I'll offset the baseband and move it off of the center frequency of the signal generator, and then I won't see that. And that's true. It'll be over here, and that will be in the signal that you're generating, but maybe that's sufficient in some cases. Normally, signal generators have some calibration to make this as small as possible, and that does a pretty good job in most cases. But you can always make it smaller by manual adjustment, usually, and but if this level is still too high, then you can use a technique like I'm showing here. Here's a quick look at the IQ modulator itself. So this is what an IQ modulator looks like, and you can think of an IQ modulator as a variable attenuator with the ability to shift the phase by up to 180 degrees. So your INQ signals go here, and you can imagine if I had DC here, that my local oscillator is going to come through here, and I'll see a CW signal out here. If there was a DC offset on Q, it would allow a 90-degree phase shifted version of the LO to arrive at the combiner, and you would also see that at the output. So that's what causes the LO feed-through. So you want to have these basically centered so that there's no residual DC here, and you want the magnitude of the I and Q response to be perfectly balanced and the same, so that you have no images at the output. And you want this 90-degree phase shifter to be exactly 90 degrees, not 89 degrees or 89.21. We're looking for 90 usually. So that's what does it and how it works. So you can imagine by manipulating I and Q, you can make any phase and amplitude of the output, and that's how we do the vector modulation. Okay, so an easy way to see how the LO feed through, how big the LO feed through is to create a simple test signal like a two-tone signal, and then you can see what's at the center frequency, and then you can quickly adjust the DC offsets to minimize that, or run the DC calibration that is available in the signal generator. Okay, so here's an example of that. Here's a signal generator that was not calibrated. You can see I did the two-tone, I made two tones here, and you can see the DC offset is very high. After running the calibration, that decreased quite a bit. So it's just a thing to be aware of. If you were generating a modulated signal here, this little guy would be hidden and you wouldn't see it, but it's still there nonetheless. Okay, so so this is, I'm just going to skip this little slide here, but it's in your presentation. Don't be nervous, just in the interest of time. We're running out of time, so I'm going to skip this. All right, okay. So I'm going to quickly click through this. So the main point here is, so I've talked about these sources of IQ error. So what are the three things you can do? So as I mentioned, you can manually adjust some of the properties of the IQ modulator to remove the images and the DC offsets to get rid of the LO feed through. You can also use this technique where I showed you can offset the modulation from the center frequency, and then you will not see the image and you would not see the LO feed through. The image would still be there, but if it's outside the bandwidth of your interest, then maybe it wouldn't be a problem. And we also have, Keysight's developed this thing called Signal Optimizer, which I'll show you at the end of the presentation. It's a way to calibrate these systems and remove the effects of the IQ modulator, and also perfectly calibrate any system, including all of the cables and adapters you might have in there, which allows you to see the true device performance. Okay, so another thing I just want to point out here quickly is that when you're using the test equipment, and you need to be aware of the things that it's telling you, particularly on the analysis side. So if you take a look at a demodulation of a signal, there's a lot of metrics that can be reported to you. So we have things that can be reported like this. Things like the amount of the DC offsets, the gain imbalance, quadrature skew, timing skew, carrier frequency offset, symbol clock error, amplitude group. All of these impairments can be reported in the software under the demodulation. Some of them are included in the EVM calculation, some of them are not included in the EVM calculation. EVM is one of these things that people are very concerned about all the time because it's sort of this single metric that gives you an indication of the modulation quality of that signal. But these things are sometimes measured and reported, sometimes they're not measured and reported, and sometimes they're removed from the actual EVM number. So even though this bad effect might be happening in the system, we exclude it from the measurement result. And that's normally because the standard is written that says this should not be accounted for in the EVM metric. But we still report, in many cases, how bad that effect is, but we remove it from the EVM calculation. So that's just a quick table that shows you really what those metrics, what those available metrics are, how they're reported and calculated, and if they're in the EVM measurement or not. Okay, some other things to think about are the crest factor of the signals that we're analyzing and generating. So here we have a signal that has this sort of this average power level here, but there's this big peak. So we have a very large peak to average ratio. And that's important for the reason of this can decrease your overall dynamic range. So I mentioned going to wider bandwidths tends to decrease the power spectral density, which makes your signal noise ratio lower. But the next thing that people also want to do is they always want to increase the modulation order. So we could do QPSK, but wait a minute, what if we did 16 QAM, or 64 QAM, or 256 QAM? As you go to the higher order modulations, or OFDM, as we go to the higher order modulations, the peak to average ratio increases. So you can imagine, to avoid clipping this signal, we have to lower the average power level so that we don't clip the top of the signal off. If we clip that signal, then our EVM is going to be impacted. So now we have the crest factor also requiring us to lower the average power level, and if it's a wide bandwidth signal, the power is also lower. So you have these two effects decreasing the signal, the overall signal to noise ratio. So just a quick test that I did with the VSA software is I measured some tones. So I took a very simple two-tone test signal with random phase, and that had a crest factor of 3.2 dB, so very small. So the CCF curve basically is way over here on the left. And you see, okay, that the range I set on the analyzer for that particular measurement was around -8, the attenuation on the analyzer to avoid clipping that signal. Then I said, what if I went to 1,000 tones? And that had a crest factor that was quite a bit higher, had 9.2 dB crest factor. And now you see this is out here and it's a little closer to Gaussian noise. So here you see there's 1,000 tones and it fills up all this spectrum, so it basically looks like a flat line, but actually that's 1,000 tones squeezed in there. Here it's hard to see, but there was one tone over here and there's one tone over there, you can barely see it. And then I said, okay, what happens if we took those 1,000 tones and instead of random phase between each of them, we kept them at constant phase? And now you can see that my CCF curve, I can't even measure it. The crest factor is much greater than 20 dB. And the range on the analyzer, to measure that without overdriving it for the same total power, I had to set that to plus 18 dBm versus the -8 that we started with. So crest factor is important metric to think about when it's important to understand how much dynamic range the signal requires in terms of,
Sorry, sorry to interrupt. Could you just explain the difference between those 1 and 2 plots? You said, I think you said one was constant phase.
oh yeah, I made a mistake here. This should say constant phase.
Okay. Yep.
These are random phase, that's a typo. Yep. Okay, so then you might say, well, that's not interesting. What about common modulation formats that we use every day? So I made the measurements for QPSK, 16 QAM, 64 QAM, and OFDM with 16 QAM on each of the subcarriers. You can see progressively the crest factor of each of those common modulation formats increases and approaches Gaussian noise when we get to many subcarriers. So what can we do to make the CCDF smaller? If we have the possibility to randomize the data in each subcarrier or the different component carriers, that can have the effect of reducing the overall crest factor. If we can add a phase offset or timing offset between carriers, if we have a multi-carrier system, that can help. And we can consider clipping the signal, but that comes at the expense of degrading the EDM, and also can add unwanted spectral issues. Okay, so this is a quick illustration that shows what we kind of talked about earlier. We keep the power constant. So here's my signal that's 1 gigahertz wide. If I double that to 2 gigahertz, then I'm going to have a 3 dB drop in the overall signal to noise ratio. And here's an example. So if I kept the power constant with a 20 megahertz LTE signal and went to 2 gigahertz bandwidth, the SNR delta would be 20 dB. So it's quite a bit different from the things we do at RF compared to what you might expect at the wide bandwidth at mmWave. Okay, so we put those two things together, the crest factor and the wide bandwidths. So here's a line showing the compression point, and we want to stay somewhere below that, and here's the overall noise level. So if we have a narrow bandwidth signal, we can have this much dynamic range, but if we're having a wider bandwidth, then our total range is going to be greatly reduced. Okay, now EVM. Is everybody familiar with EVM? No, let me ask it the other way. Who's not familiar with EVM? Yes, yes? Okay, we'll do a quick overview of that. So EVM stands for error vector magnitude, and is a measure of the quality of the modulation of a signal. So here is the signal that I'm generating. I want to position this signal at some particular amplitude and phase at a given moment in time. And I want to measure how close did I get to the desired amplitude and phase that I was trying to go for. Here is the correct amplitude and phase. So this is our IQ reference. So normally the test equipment can measure the signal, and based on what it measures, it can work out what the ideal reference should be, and then we can calculate the difference between the ideal reference and where the signal actually landed, and that is the error vector in the amount of the error in our signal. So this is a single metric that takes into account many different types of errors and gives a measure of the overall signal quality. Let me skip that. So we could say in a system, particularly when we get to these wider bandwidth systems, the EVM is usually dominated by the noise. And so the EVM is basically equivalent to the SNR available in the system, plus or minus 3 dB. Each radio format defines how the EVM should be calculated, so there's some different things to consider when we talk about a radio format. We have some frame structure that has maybe some pilots, some preamble, the data portion. Is the EVM measured over all of that or just a portion of that? So, and each standard may do that differently. Usually the carrier frequency error is always removed, but we always report that so you know how large it is, because that would completely correct the EVM number, unless it was exactly perfect. Usually the DUT channel response is removed from the measurement, from the EVM measurement through the use of through an equalizer. Not always the case, but usually the case. If we look at the constellation, OFDM and single carrier constellations can look greatly different depending upon the types of errors that are causing that. We have a whole app note that goes into those intricate details that you can look up on our website, so I won't dwell on that here. But there's a lot of things that go into an EVM measurement. Let me just check the time here. What time is it?
4:37.
4:37. Okay, so what I think I'll do now is stop with so that's a quick overview of the EVM and why that's important. There's different ways to measure this, and there's no necessarily one right way to do that. But the standards usually define exactly how this should be done. So sometimes you can compare an EVM from this standard to that standard, and the number, the actual error could be very similar, but the number very different because of the way the calculation has been defined to be done. And you also must be very careful when making comparisons of generic modulation where there is no standard, because this group made these assumptions and this group made these assumptions, and if those assumptions aren't exactly the same, you're not comparing apples to apples, and that will cause issues. So what we're going to do now is I have another guest speaker who is going to do a little interesting demonstration that illustrates some of these concepts, so we can model a number of these different errors with software, and allows us to see what is the effect of changing some of these things. How does that affect the EVM? How does that affect our overall system performance? So with that, I'm going to bring up Mr. Greg Jew, whom you may or may not know, but he's an expert on this thing called System View, which he will use to illustrate simulation. So can I move you? You can. Yeah.
Okay, so hi everyone. My name's Greg Juice. I work with Randy on mmWave applications. Prior to doing that and several other jobs, I was kind of working with the System View team and simulation. So we thought it might be kind of useful to kind of illustrate some of the impairments that Randy had been talking about. You know, you guys are probably building real hardware systems, and many of the impairments that Randy's been talking about are going to be very relevant to kind of your day-to-day job in putting together these systems. So we took a very simple example in simulation. It's not necessarily representative of the type of systems that you design, because they're likely to be a lot more complex. But basically, this just involves kind of a source, an OFDM source. In this case, I think it's 802.11ac. And then to this, we added a LO and an IQ modulator, so we can illustrate some of the IQ impairments that Randy had talked about. We have an amplifier. Right now, you'll notice that it has kind of a green X through it, which means it's basically a short circuit. So when I do the simulation, it's not actually going to contribute anything to the simulation initially. This noise density element is just adding KTB, so minus 174 dBm per hertz. And then to do the simulation analysis, we have our VSA simulation element in here. But you'll see when we bring up the display, even though it's measuring simulated signals, it's the same analysis software that we're showing out on the show floor for doing our demodulation for our P5D waveforms. So let me go ahead and I'll just do a simulation to kind of give you a feel for what the baseline will look like, and then to this we'll start layering different impairments so you can kind of get a feel for how these different impairments that Randy's been talking about impact EVM and constellation. So this is kind of our baseline, and it's very ideal. It's not necessarily representative of what you'd see on the bench, because on the bench you have real signal generators and analyzers. They have their own sources of impairments. But here we're kind of in simulation land. We can set things so that they're fairly ideal. So we have our 64 QAM constellation, we have our spectrum, and our baseline EVM with the phase noise settings that we have for the LO is about 0.7. And then we have a CCDF curve here, which kind of gives us a feel for the statistical peak to average properties of the signal. So if you can't see the EVM because maybe the color scheme isn't the best choice, just kind of lock in your mind that we're starting out with about 0.5% EVM. So let me go ahead and I'm going to stop this and let's add some IQ impairment. So Randy kind of talked about, with signal generators, typically we have baseband IQ going into like a SIGGEN. You have to worry about IQ offset, gain imbalance, phase imbalance, that sort of thing. So let's just take a IQ modulator, and to this we have a gain imbalance, which has gain imbalance in terms of dB. So let's just start with 0.1 dB. See how that impacts the constellation and EVM.
Wait for it.
Wait. Okay, so you might not see it on the constellation, but EVM's increased up to about 0.8%. So we have some degradation as a result of this gain imbalance. Let's just make this a little bit more severe. Probably this is going to be a little bit extreme, but let's just show it. So I changed the gain imbalance to 0.5 dB. And so now you can kind of clearly see some dispersion on the constellation as a result of the gain imbalance. So if you were working with analog modulators, this is something that you would need to be concerned with. Likewise, if we add some, let's drop this back down to 0 so that we can isolate this error. And let's say we had 10 degrees of phase imbalance, which again is probably pretty extreme. It's probably going to destroy our constellation, but let's just check it out and see if that's actually the case.
You didn't try this beforehand?
Didn't have time, I was doing demos on the floor.
Oh.
Yeah, so that was a bit extreme, but clearly you see that any sort of gain imbalance can impact the performance as well. So we have to be pretty careful about dialing these in, maybe doing some calibration if we were generating a signal with a signal source. And then likewise, if you have an analog IQ modulator in your system, in the transmitter part of your system, you would be concerned about this as well. So let's reset this so that we're back down to the baseline, and let's add phase noise to the setup. So I have an oscillator here. This is just being used for the IQ modulator, but if we're doing some sort of heterodyne system, we might have some mixers with LOs. I think Randy's probably talked about, phase noise can be very important, especially when you get into these high-band mmWave systems where you have to have a pretty high LO. So you have to have good phase noise to start with, and then you have some 20 log degradation of the phase noise